record. Conditional statements. What are conditional statements? So a conditional statement is basically a statement that can be written in this form. If P, then Q. P and Q aren't just letters in this case. They're standing in the place of statements. Importantly, it's an important part that these two statements, P and Q, can be determined whether they're true or false. That's something that's really important about conditional statements. We want to make sure that we're very concise in our wording of them so that it's easy to determine things are true or false. So if we look down here at the bottom of the screen, you can see two examples of some statements that are pretty easy to decide whether they're true or false. So we got down here, we got today is Friday. Easy enough. That one is currently false. It wouldn't always be false, but currently it's Monday, so that would be a false statement. And the angle is obtuse. Well, in this case, if we knew what angle we were talking about, it would be easy to decide if this was true or false. So if we had an angle that was, I don't know, 130 degrees, then it would be easy enough for us to determine whether that was a true statement or not. And in this case, that would be true. But again, depends on what we're talking about. These statements that we use to build a conditional statement need to be easily verifiable. We can look at them, we can decide, is it true, is it false, how does it go? You don't want any ambiguity, any unclearness in it. It needs to be very clear whether we can decide if something is true or false when we're working with conditional statements. All right, so let's look at an example of first we're going to talk about why we use conditional statements. Clear that. So why do we use conditional statements? Well, in math, we use conditional statements to write theorems, corollaries, lemmas, and many other important math type things. So when we start building up more information that we know about geometry, we're going to be creating a lot of theorems and showing a lot of theorems. And so an example that we kind of already know about is something called the linear pair theorem. This is the linear pair theorem, and it's written as a conditional statement, as an if-then statement. If two angles form a linear pair, then they are supplementary. So hopefully you remember that a linear pair is something like this, where you have two angles that together make a straight line, right? That's what we mean when we say linear pair. So if we call this angle 1 and angle 2, we know together they form a straight line. Well, when you make a straight line, that means that it's 180 degrees, right? The measure of a straight line is 180 degrees. So this is a true conditional statement about linear pairs, which is why we call it a theorem, because it is a true statement. All of our theorems are going to be written in some ways like a conditional statement, or they could be at least phrased in that way as a conditional statement, even if they're not written that way. So when you read a conditional statement, it's important to know that it has kind of an order to it. It has an if and then a then. And when you read it, what it's saying is if this first part is true, then this second part has to be true. So if we have a linear pair, then we know that the angles have to be supplementary. There's an order to it. It doesn't mean that it has to work both ways. Conditional statements can kind of be thought of in two different ways, but really we only read them in one direction. So this one only has a singular direction. Okay, so let's talk about the parts of a conditional statement. No, examples. I'm a little bit out of order here. All right, some examples. So here are a couple examples of some conditional statements that we can just kind of look at and read. So if an angle measures more than 90 degrees, then the angle is obtuse. Okay, that seems reasonable. If today is December 22nd, then it is winter. Again, what I really want you to notice with these particular conditional statements is, while one of them is really technical and mathy, the other one is a little less, a little something that's maybe easier to understand. They're both, each part of them, the if part and the then part, is very easy to determine whether they are true or false, right? It's really easy to decide if today is December 22nd. It's not, right? So it's really easy for us to make a decision whether that part's true or false. Same idea, it's really easy for us to decide whether it's winter. Winter has a set definition. It's between some certain dates of the year, and that's what we call winter, at least here in the northern hemisphere. We could get technical and say, well, technically in the southern hemisphere, it's actually spring or whatever, right? Things work a little differently. But it's easy enough to verify any part of this, whether it's true or false. And that's really important for conditional statements. They have to be easily verified, true or false, one way or the other. All right, so we can break down each conditional statement into two parts. The first part is called the hypothesis. The if part of the conditional statement, it's called the hypothesis. So right here we have the if part. So if today is Tuesday, this is our hypothesis. Oh, I went to the wrong screen. They look so alike. Sorry. The if part is the hypothesis. If a polygon has 4 sides, then it is a quadrilateral. And this first part is our hypothesis. Again, very easy to verify whether it's true or false. We can look at the polygon, the shape, and decide if it has 4 sides or not. If it has 3 sides, our hypothesis is false. If it has 4 sides, our hypothesis is true. Those are just examples, but we can easily decide whether our hypothesis is true or false, for a given situation at least. All right, and then the second part, we call that the conclusion. So the then part of a conditional statement is called the conclusion. So for the same statement, or for a different statement we have right here, the then part is called the conclusion. This conditional statement is a little more vague and not as clear how we would decide some of these things, but it's still a conditional statement. It's written in if and then, but you might be able to see how it's maybe a little more vague. If today is Tuesday, that part actually is pretty straightforward. We could decide whether today was Tuesday, which again, right now it's not, but that doesn't mean it'll always be false. In fact, right tomorrow, this part would be true. The conclusion, though, maybe that's a little vague. We'll have tacos for dinner. We could argue maybe what constitutes a taco or what constitutes dinner or things like that. It's maybe a little less concise. Generally, when we're working with conditional statements, we're going to work with very specifically mathematically defined things, like a particular kind of shape or a particular property that is very clearly defined, but it's easy enough. We could probably verify this to be true or false also. So this is our conclusion, the second part, the then part. We're starting pretty basic. I just want to make sure everybody kind of understands what the different parts are. And I'm gonna clear that. All right. Truth value. So this is kind of a big deal for conditional statements. And I've already sort of talked about whether statements are true or false, but each part of a conditional statement, the hypothesis and the conclusion, will have a truth value. So T for true or F for false. That's the way we'll shorthand it anyway. No TFs. You don't want to use any of these letters that people do sometimes when they're given a true false test, where they're like, yeah, it's like a TF. It's a true false. You know, it's going to be clearly one thing or the other. It's true or false. So we need to be able to identify whether the hypothesis is true or whether and whether the conclusion is true or whether they're false or what their values are, because we decide whether an entire conditional statement is true or false based on the hypothesis and conclusion. So what we have here is a conditional statement will only be false if the hypothesis is true, but the conclusion is false. This is what we're going to call a counterexample. So that silly conditional statement we had from the previous slide, if today is Tuesday, then we will have tacos for dinner. A counterexample would be, it is Tuesday, that part's true, but you have something else for dinner. You have pizza or salad or something else like that. That would be considered a counterexample, and we could state that the entire conditional statement was false because of that counterexample. We'll get more into counterexamples and how to come up with them and things like that in a few minutes. Okay, I'm gonna go ahead and move forward. All of this is available on the Google Classroom page, so you don't need to panic to write everything down. All right, so let's go ahead and look at these 4 statements. These are not conditional statements. They are things that might be used as part of a conditional statement, like the hypothesis or the conclusion. So I'm going to number these. Go ahead and look at them and see which ones of these are true, which ones of these are false. Figure out the truth value. Should be pretty quick. So do me a favor in chat. Number 1, is it true or false? What do you think? Today is a school day. Cool. Getting a lot of trues. I agree with you. I mean, we are meeting with each other, so I'm assuming we agree that today is a school day. So that statement is currently true. There's nothing we could say to argue that. Is it always true? No. Yeah. So this is a statement that, depending on the day, could be true or false. It varies. It is true, though, currently. But it could vary. It could be false. If it was Saturday and you were watching this, you would say, oh, no, that's false, right? But right now, it's true. All right, number 2, cats are mammals. In the chat, what do you think? Cool. I'm seeing lots of trues, and actually I see something that's really important in there, that it is true all of the time. Someone said that it's true all the time. So this one is an example of something that is simply always true, or at least to the best of my knowledge. I don't believe there are any cats that are not mammals. I'm pretty sure all cats have live births and have fur and feed their young milk. I don't know that that's all of the distinctions for mammals, but I think that's most of them. So all cats are mammals. What about number 3? False right now. Currently false. So this is one of those situations where it kind of depends when you're asked the question. Could be true, like a few weeks ago, right? The 21st or 22nd of September was the first day of fall. So just like 3 weeks ago, we would have said yes to this. But right now, false. Or we could even say, I'm seeing in chat, for us, it's false. Actually, the southern, no, it wouldn't be the summer for Southern Hemisphere either, right? It would still be like spring or something. I don't know how that works, not being a resident of the Southern Hemisphere. But yes, it is currently false because summer usually follows sometime from mid-March to mid-September. So currently false, sort of like the first one, right? It just sort of depended when you were asked the question. And then the last one, what do you guys think? Number 4. True, false. Seeing mostly false. I'm seeing a true for me. I'm seeing depends. Yeah, this is a statement that obviously depends on who's reading it. It's different for any person that was asked this statement, right? It could be true or false, just depends. So I kind of wanted to show this here just in terms of the different types of statements that we can have. We can have statements that are true for a given circumstance, like right now, today, it's true, or false for a given circumstance, like right now, it's false. We could have things that are always going to be true or always going to be false, or we could have things that are a case by case basis. It's true for some people, false for some people, true for some things, false for some things. All of our statements can kind of have truth values that work in this way, right? So it's important to be able to think about all of the possibilities when we're evaluating the truth value of a particular statement. Now, for the most part, we want something more like 1, 2, or 3, that it has a more set state, like currently this is true, or currently this is false, or it's always true or always false. This sort of vagueness where it could be true and false at the same time for different people is a little less clear. So we won't have a lot like number 4, but it could come up. All right. Counterexample. I already sort of briefly mentioned this, but when we're talking about the truth value of an entire conditional statement, a whole if-then statement, we are looking for what's called the counterexample. If there's a counterexample, only one counterexample, then a conditional statement will be false. If there is no counterexample, then the conditional statement will be true. And so the counterexample is this. Hypothesis is true, conclusion is false. So when we read a conditional statement, we need to think about, is there any way that the first part could be true, but the second part is false? That's our counterexample. It's much easier to prove that a conditional statement is false because we just show one counterexample. That's it. That's all it takes. One counterexample, and we have a false conditional statement. It's harder to show that a conditional statement is true because what we have to show for something to be true is that it's impossible for there to be a counterexample. There are lots of ways that we could do that. We could maybe think of all the possibilities and show that all of the possibilities work. That's one way, but that's pretty exhausting. There could be, in some cases, there could be an infinite number of possibilities. We could create a equation of some kind that represented our conditional statement and show that that equation works out for us. That could be something that would show it's true. But the point is, it's just much harder to show that it's true because we have to account for every possibility and show that there cannot be a counterexample. So showing that something's true is going to be harder. All right, let's see what we can do with this. So here we have a conditional statement. We have if x squared is equal to 25, then x equals 5. So this is our hypothesis. Yeah.
If it says I leave, I'm not leaving. My Wi-Fi is just cutting out really bad, and it keeps kicking me out of Zooms all day. So
That's fine. Thank you for letting me know. So this first part, if x squared equals 25, that's our hypothesis. And this is our conclusion. For a counterexample, remember we need this part to be true, but this part to be false. So we want to come up with a number that is not 5, but does make this equation true, but is squared does equal 25, right? We want this part to be true, this part to be false. So something that's not 5, that satisfies that. And I'm seeing it. I'm seeing the answer in the chat. Yeah, x squared equals 25. If we do negative 5 squared, that is indeed 25. So that works. It's a true hypothesis, but it's not 5. It's false here. It's not equal to 5. So negative 5 is not equal to 5. So it has a true hypothesis and a false conclusion, or at least a conclusion that is different than the one here in the conditional statement, right? This one's pretty, mathy. It's an equation. Some of them are going to be like that. Some of them are going to be a little more vague, a little more thought that's needed to go into it. But in this case, yeah, easy enough. We came up with a counterexample. We showed we could have x squared equal 25, but not have x equal 5. So that's a counterexample. Hopefully that's pretty clear there in terms of how that worked. Okay, I'm going to go ahead and clear my writing and do this. Okay, so what I want you guys to do is to try to decide whether these two conditional statements are true or false. So I'll give you a few minutes to read the statements and think about them and see if you can come up with a counterexample or not. And feel free to put it in the chat. It's fine. Yeah, if you want to put your answers in the chat for 1 and 2, that's okay too. I'll talk about the answers in a couple minutes, like 2. So seeing a lot of good answers in the chat. If you do say that one of them's false, will you give your counterexample as well? So I'm seeing a lot of good counterexamples for number 2. That one's the easier one to start. I mean, it's just the easier one in general, I think. Maybe not, but that's my thought on it anyway. So I'm seeing a lot of people coming up with different numbers that would work. So the number 2 is an even number. It's not divisible by 4. Really quickly, in math, when we say divisible by a number, what we mean is that it divides evenly. When we do the division, we get a whole number. So like 8 is divisible by 4, because if you divide 8 by 4, you get a whole number. But like 10, for instance, would not be divisible by 4, because when you divide it, you either get a decimal or a fraction. So divisible by means you have to get a whole number. So 2 is a counterexample. Just from the chat, I'm seeing 14, 6, 10. Actually, in this case, if you think about your even numbers, if you just kind of go through them, every other even number is a counterexample, right? 2 is not divisible by 4. 4 is, so that one works, but 6, not divisible. 8 is, but 10, not divisible by 4. 12 is, we'd get 3. 14, that's not divisible by 4, right? So technically, there's actually an infinite number of counterexamples in this case. We don't need that many. We only need one counterexample, but it's good to know there are a lot. So these are all counterexamples. And remember, they are counterexamples because they're even. They satisfy this first part. This first part is true, but they're not divisible by 4. So they make this second part false. Just trying to be clear with it. I know that it seems like most people get it, but all right, I thought this one was a little harder, but everyone that's put an answer in looked like they got it right. This one is going to be true. When things are true, in particular, if they're kind of mathematical relationships like this, it's important for us to think about the definitions of the terms that we're dealing with. So what does it mean to be acute? And what does it mean to be supplementary? So keeping those definitions in mind and what that actually means, right? So acute means that it's between, so our angle is between 90 degrees and 0 degrees. So it's greater than 90, but it's less, or sorry, greater than 0, but it's less than 90. Strictly greater and strictly less than in this case, because a 0 degree angle is not acute and a 90 degree angle is not acute. It has to be in between those. And then supplementary, of course, means adding to 180. So we could probably come up with some sort of equation or inequality or something that might help us here, but it doesn't really matter. What I want to think about is sort of the extremes. Like, what's like the biggest acute angle we could have? I mean, technically we could go bigger than this, but like this is pretty close to the biggest acute angle we could get, right? 89.9. We could go even closer. We could do like 89.99 or 89.999 or whatever, but that's close. If I add two of those together, I'm still not going to get 180, right? I'm going to get like 179.8 if I added those together. So it's not going to be 180. So it's not supplementary. So if the first part is true, the second part is still true in this case. So that's not a counterexample. What I want to illustrate by this, talking about this way, is a lot of times when you're trying to prove conditional statements true or false, thinking about sort of extreme examples for your hypothesis. So like the biggest acute angle you could have, or the largest perimeter, or something that's on the extreme end, the highest end or the lowest end, might help you. It might be where you find your counterexamples, or it might be where you're able to show that you can't come up with a counterexample. It's a helpful way to start thinking about these problems anyway. So anyway, even sort of the biggest acute angles we could come up with still won't be supplementary. So that's still true. So this is a true conditional statement, because really to get 180, we would need a 90 and a 90. And a 90 and a 90, that doesn't work for the first part. That's not a true hypothesis anymore. So that actually doesn't work for us. All right, let me check the time. 58. We have 2 minutes, so I'm going to stop right there. Tomorrow we're going to talk about more about conditional statements and Venn diagrams and some other things. But I want to bring our attention back to